Well, hello, dear guests. Well, I think that we should start. I see already around 30 participants on our today's session. I hope the other people will join us in a couple of minutes. Well, hello, I'm Nikita Tokarev. I'm director of March Architecture School in Moscow. And I have a pleasure to introduce you our today's guest, our today's lecturer, Lucio Blandini, from Stuttgart, director of the Institute of Lightweight Structures in Stuttgart. And I have a special pleasure to introduce Lucio today, because first of all, we're collaborating with ILEC, with Institute of Lightweight Structures during many years. We started it in 2015 when we launched our undergraduate course in March. And Professor Werner Sobek, who was a director of ILEC at that time, agreed to help us to make a structure, technologies, and materials course in our undergraduate program. And we're still collaborating with Werner Sobek's office and with ILEC, well, in the frame of our undergraduate course. Well, this is very good for us and for our students as well. So we see that the history of our common joint work is already quite long now. Well, and another point, what I wanted to mention is that now, well, in this moment, there is an exhibition in Moscow, in center of avant-garde in Shablovka, very near to the great monument of lightweight structures of Shukhov Tower in Shablovka. And this exhibition is actually made by our students and tutors. It is a result of exactly this module of structural technology, structures, technologies, and materials of our bachelors. They did last year. They did very nice models and research of different structures in the end of 19th century or in the beginning of 20th century. And our today's meeting, our today's lecture is inside the public program of different discussions, lectures, other events along this exhibition. Well, that's why I have three points of pleasure to introduce you our colleagues today, Lucio and ILEC in Stuttgart, and our partners as well. Well, hello, Lucio, and I give a word to you now, well, to talk a little bit about the matter of facts, the matter of lightweight structures. We are working with our dear students and tutors. Well, thank you very much. You are welcome to our public program.
So thanks, Nikita, for the kind introduction. It is a pleasure for me to continue on this line of collaboration that, as I will explain later, as even longer route in the scientific work on Shukhov that has started as a collaboration already in the 90s, that means 30 years ago. But let me share the screen with my presentation so that we get in the depth of the topic for today's presentation. So I hope you can all see my screen. Great. So my lecture today is about lightweight structures, matching the exhibition that is ongoing in Moscow. And it is about its root in the past, its current development, but it's also trying to give a view, at least from our perspective, how the future of lightweight structures could be, and of lightweight system in general, given the challenges we all have to face in architecture for the coming years. But before we get into the historical development of lightweight system, I would just like to go on the principle of lightweight. What we do understand as lightweight, how many fields we see and what sources of inspiration, because lightweight covers a really wide field. And actually the very first source of inspiration is the nature. It is not always like that, because the nature is not always following principle of lightweight system. But when we look to what a spider can create in terms of a lightweight system, then this is an interesting source of inspiration, and it has been for a long time. And I'm not only referring to the capacity of creating a very light web, but I'm also talking about the capacity of tuning the different performances of this web depending on what the performances and the targets are. Since this net is changing stiffnesses and is changing capacity depending on the kind of insects that has to trap, depending on the energy that it has to absorb. So it is a very, very complex behavior, which is actually scientifically not easy to be modeled, but it's a good source of inspiration. There is a long tradition of lightweight system in the automotive industry, and since we are following an historical path, I wanted to show this Holder race car made from Ferrari right after the World War, just as an example how complex systems can be simplified, reduced, and by this kind of process optimized in order to minimize the amount of resources. At that time, it was about reducing the fuel consumption, but today this approach has different consequences and interesting aspects linked to it. And on a similar perspective, we have a source of inspiration from the aeronautical industry, and the Concorde at the end of the 20th century was for sure a source of inspiration, pushing the boundaries in terms of material capacities of what a system can allow for. So high temperatures, resistance to high velocities, and all of that was possible by making a very careful use of materials by combining them in a careful way. And today we see lightweight principles adopted in the sport, especially in the racing sport industry. And here, just as an example of many, the a sail ship, which has been reaching a Guinness in terms of velocity, exactly by using lightweight approach and combining materials and design in a proper way. And interesting enough, just to bridge to what I will show later, we are currently working with a sale producer to transfer part of their technology into architecture. But I will show something more at the end of this presentation. So there are a lot of links between different fields, and actually lightweight lives out of this interdisciplinary approach, since it merges together different fields of interest. If we want to break down to few rules to be followed, and you will see links to the work of different architects and engineers I will show later on, we can say that working on lightweight, it's about minimizing the amount of material to transfer forces. And in order to do that, it is very important to use structural sections, to use materials in an optimized way. That means so-called fully stressed design. So this means that we are always trying to use elements in fully tension or in fully compression modus. And even if you have systems that are subjected to bending, there are ways of dematerializing those and in truss systems, so that each of these truss elements is again working efficiently. At the end of the day, when you are working with a lightweight approach, it's not about designing components. It's not about designing columns or slabs or walls element and componing them together. It's about designing stress fields. And this is what it makes these areas challenging, but also really interesting, because the forms, the optimum forms or the possible forms that are part of the investigation. So it is an open search in a way. And in this research, we have to keep in mind that we have some physics rules that we have to follow. So if we are working in tension, we can bridge long distances. But if we work in compression, we have to bridge short distances. Otherwise, we have issues of instabilities. And if we are able to shortcut forces, then this will lead to an optimal use of materials. So once at that, we can go through a kind of historical paths over the last, let's say, 140, 150 years, starting with pioneers that at the end of 19th century have been dealing with different materials and trying to make an optimal use of that and reducing amount of resources. There's been a generation at the end of 19th century, it was the start of the Industrial Revolution, dealing with steel and discovering the potential of steel and finding out that, like in this case, Gustave Eiffel did for a bridge in France, that by using truss systems, the amount of material could be a lot reduced. And this is essential because, especially for big spans or big height, reducing the amount of structural materials means being able to span or to achieve bigger spans or to reach higher heights without achieving that the structural dead load is becoming determining. And even if we look at one of the most beautiful examples of this time as the Eiffel Tower, reaching at that time 300 meters, I would like then to point out that Shukhov was working on systems that were able to achieve much better performance in terms of weight to height. So it's a pity that it has not been possible to build this 300 meters tower, but it is the kind of motivation to push the boundaries of lightweight, because that makes a big difference when you have to span such or to achieve such heights. And what I find very interesting is that at that time, at the end of 19th century, Shukhov was working for a contractor, and it was this tight collaboration with the manufacturing industry, and the scarcity of resources at that time, helping to push the boundaries. In this case, with a tension. Mainly a roof which is mainly subject to tension forces. And by doing that, by having the forms shaped by the way the forces are acting, it was possible to reduce the amount of materials, which was very effective. And here, the power line, which is still nowadays almost 100 years after that they've been erected, it is an astonishing example how elegant the system is, not only in the final appearance, but also in the process of erecting that in an efficient way. And I think this is what we need again today to shorten the chain between design and construction to come to new ideas how today such kind of resource efficiency can be achieved. So the past is not only an element to be looked at, but also a source of inspiration. And this is the kind of spirit that I put this, this presentation together. So when we look at, for instance, at this bridge from Robert Maillart, it is incredible to see how at that time, not only the form has been optimized, but also the construction sequences have been optimized to bridge this this area, and it is still has after such a long time an incredible elegance in the in his form and in his capacity of getting embedded into the nature. It's interesting that after that the most talented engineers have been challenging themselves with the use of steel. In the first half of the 19th centuries, the challenge has been shifted to concrete system, and then the interest has been shifted more from truss and tension element into compressed elements, or into element compression, just because clearly concrete has a very good capacity to resist compression forces. And on top of it, it's a very good capacity to be shaped in a proper way, following the forces. So there's been a kind of competition between different engineers at that time. And you can see what Torroja has been doing then 10 years or a few years later than in Madrid, with very, very thin shells, concrete shells. This has been renovated recently, and you see how modern and elegant it's still looking like. And still, it was not only dealing with concrete, but also dealing with possible combination of concrete and steel, combining the properties of these materials. And I believe this is one of the keys of lightweight system nowadays, not to focus only on one material, but to combine the properties of different materials, and the heart is to join them properly. If we move further to the experience carried in Italy, then we have one master engineer also of concrete structure, and this Pier Luigi Nervi, working during in the wartime to create this very elegant and slender shell system as rib system. And interestingly enough, also Nervi was working as a chief engineer in a contractor company, as Shukhov was doing. And again, this tight connection between engineering, design, and construction made possible to push the boundaries and achieve the kind of filigree character of this elements. And one of the later results of this work, so-called ferrocemento, which is concrete with a high degree of prefabrication and a high degree of steel element, and can achieve following the paths of the forces. So remember what I was saying before in terms of stress fields and designing stress fields. So this is a clear example of that, which is materialized into an astonishing architecture, which is still visible. And I was there 20 years ago as before starting my career as an engineer, and it was astonishing to see how beautiful this roof is and how inspiring this work is. But still, we cannot just look to the past. We have to think how these examples can be reinterpreted today. And that's why I'm following on what is happening, starting from this experience in Stuttgart. And I would like to start with a contribution from Fritz Leonard, which I would say is one of the first persons that brought this interest for lightweight system in Stuttgart, taking inspiration from nature, as you can see in this publication, which has been, by the way, written in 1940, and taking inspiration from nature. At that time, Fritz Leonard was just 31, and he was trying to push again the boundaries and explain how important it is to use a different approach to the building world, and that was during the war, if you want, and make a proper use of resources. At the time, as it was in Russia then before, it was about resource optimization, but this is still an approach that nowadays is very relevant. And this approach has been leading him to very interesting application of pre-stressed concrete. So it was, in a way, a combination of the capacity of concrete to resist compression and the capacity of cables subjected under tension to integrate and to compensate part of the concrete behavior in order to get a combination, an optimal combination of the two materials. So pre-stressed concrete on one side, and Fritz Leonard is one of the father of this technology. But as you can see here on the television tower in Stuttgart, also the capacity of dematerialized the base area of this tower over 200 meter high by having a base element which is translated into a truss system by conical surface. So you have an exterior cone and you have an interior one, and you create every time then triangular, which are very stable. And what I still think it's an amazing image is the drawing of the tendons at the basic, which are then pulling all the base together and making sure that there are very little movement in the system, and that everything is tied together. And following to the development of the integration between tension element and compression, he has been designed over a long time bridges all over the world. I just pick one over the Rhine in Germany, which I believe is very elegant, but it's just one of several examples. And the company that he founded is still very successful in generating that. And what I believe it was very specific to Stuttgart, it was the capacity for each generation to invite other people to join them and to continue this path and this search for lightweight systems. So we've been looking into steel system, into concrete system, into trusses, into tension element. The geometry of that was already pretty complex, but by the fact that Frei Otto has been invited from Fritz Leonard in the 60s to join him at the University of Stuttgart as professor for lightweight system, Frei Otto was trained as an architect, but was following a very, very personal and specific path. The formal research in terms of lightweight systems have reached a completely new level of complexity, and this is due to the fact that Frei Otto was very interested in the use of several experimental paths to find new forms. And one example is the approach with soap bubbles, which are delivering minimal, so-called minimal surfaces, which is a basic for new research of forms. And what you saw before is nothing else than the basic for the development of the institute, how it is right nowadays. At that time, end of the 60s, it was just a prototype for the Montreal exhibition. But then this prototype in a scale 1:1 of a small part of the Montreal exhibition was so interesting that it has been converted into the institute. And funny enough, more than 50 years after that it has been erected, it is still an amazing place to make research. And people are still astonished and fascinated by the capacity of this space to still inspire new ways and new approaches. So you see what all this prototype work was made for. Here is the SciNet cable net system for Montreal, for the German pavilion. And what I would like to show is that this approach and this research of forms, it was not only related to a tension element, but it was also related to the possibility of using these forms for compression elements. And that has been turned also as a cable system reverted. It is an approach that already Gaudí was using in the past, but it has been brought to a totally new level of quality from Frei Otto and then used for the multi-alloy in Mannheim in Germany in 1975. And the interesting thing in my mind is that he was not only looking into experimental form, but he was looking in a wide spectrum of natural processes and trying to learn from that. It is not about copying nature. It is about using the nature as a source of inspiration, because nature is not always following the target of optimizing amount of material. There are different targets, and you can always understand them and reinterpret it if you go deeper into their behavior. And there's been a big research project for several years with contribution of several scientists trying to understand how the nature can be used as a source of inspiration for nature, for architecture. And one of these investigations was the investigation about branching processes. Some people are talking about tree systems. I believe it's not that much about trees. In a way, it goes beyond that, because also trees follow different rules than just resource optimization. It's also about optimizing the amount of light exposition, and it has to do with growth processes. But still, there's a lot of examples of branches and branching aspects in natural processes, and this can be extrapolated and translated into architecture as it has been done in the Stuttgart Airport done in the early 90s. And in the 90s, there's been what I was referring to before. There's been a very fruitful collaboration between Russian and German scientists exploring the work from Shukhov. And I was reading that in the past as I was a PhD student, and I was reading it again in the previous weeks. And it is still amazing how much we can learn from these past experiences. Let me now focus for a second on the Olympia Roof in Munich, since this is, I think, one of these cases where several generations of people have been coming together in Stuttgart and allowing for something very special to happen. And if you see how complex this whole landscape and this whole architecture is, that was at that time, it was just the architectural model. But to translate that into built architecture, there was a long and very pioneer process. And it required, with the tools that were available at that time, required a lot of methods that have been developed in Stuttgart, starting from advanced modeling strategy into possible translation of these models through photogrammetry, into geometrical description, into the early tools of calculations of this. And you can see part of this experimental work also involving the work of geodesy experts. You see here photogrammetry approach, all things that nowadays can be solved in a much more advanced way with more sophisticated tools. I will show some of them later on in more recent projects. But the more you think about that, the more you can admire the pioneers, the spirit, which this has been done 50 years ago, and leading to that kind of complexity in terms of geometry. This is the cabinet. And you see here together some of the most important exponents at that time. You see the third person from the left is Frei Otto. The one which is leaning to the wall is at that time young Jörg Schlaich. He was less than 40 years old. Next to him, Fritz Leonard, which I was talking about before. So, and several others which were bringing, or which in these pictures in my mind makes visible this idea of a school, which is not only just a school of a classical academia, it's really a school of thought where these people show that bringing together in a tight way praxis, experience, willingness to push the boundaries, and scientific research can bring to astonishing results. And the result is one of the masterpieces is the Olympia Roof in Munich. And you see on the left how Jörg Schlaich and Fritz Leonard as engineers were making the complex behavior of this cable system pretty easily, if you look at closer, readable. I could talk long about that, but it would not fit into the time frame. So you can read a lot about that. It is now just about how you can reduce complexity in such a way that you can keep control of that and achieve very, very inspiring architecture out of it. And if we move now to the work of Jörg Schlaich, from the field of tension structure into the field of structure under compression, then you see how shell structures, keep in mind what we saw in concrete at the early 20th century. Now we see the next generation of shell structure in a more modern and dematerialized way as a glass and steel structure done in 1989. And also here you can see combination of tension structures and compression element, as we saw in the work of Fritz Leonard, but brought into the next level, as it is visible for the Maxai See in Stuttgart. And interesting enough, a lot of these details have their root in the research work, in the scientific work that has been carried at the University in Stuttgart, to allow for the Olympia Roof to be built with a good with a high level of safety, even if there was a lot of experimental work behind that. And further works on tension structures, of course, include a big stadium. It's a field where Jörg Schlaich and his team have been, I think, pushing a lot the boundaries over the last decades and leading to very interesting results. And if we move to the next generation, the scholar of Jörg, or the favorite scholar, if you want, of Jörg Schlaich was Werner Sobek, started working in his offices at the end of the 80s and working with Jörg Schlaich together on this pneumatic system for the arena in Nîmes. A deployable system which can be folded or can be compacted pretty easily within few days and then deployed again to achieve a working roofing system for this arena and making this historical piece more usable than over the year. And here, a new interpretation of cable net system in the Rhone Clinic, based on the fact that one typical detail that allow for different shapes and different cladding elements to be achieved can be the basic to make this idea of the tent. You can see a bridge to the early work of Shukhov I showed at the beginning, but reinterpreted in a totally different way. And this is actually the way that we can keep reinterpreting and reinventing lightweight approaches and principle over the time. And here in the airport for Bangkok, one of the most important achievement of Werner Sobek, you can see how trusses can be reinterpreted in a very, very elegant and in a way iconic way. And Mutian, who was responsible for the architecture, has passed away, unfortunately, a few days ago. But I think these masterpieces remain as a documentation of what can be achieved. And one of their last shared work together, Werner Sobek and Mutian, were responsible as architects for this astonishing tower, very elegant. It's an experimental tower for elevators, high-speed elevators, with a high level of elegance, bringing a tension element as and fabric as a facade system, allowing a much better shadowing capacity of the concrete tower behind it, and overcoming some of the problems that were visible at the television tower, which was engineered more than 50 years before then by Fritz Leonard. But as I was saying, the Stuttgart school was based on the tight connection between practice and research. So let me explain a little bit about the research that was carried also by Werner Sobek at the ILEC, which following up to the work from Frei Otto done before on one side and Jörg Schlaich on the other side. So Werner Sobek has merged these two paths in a kind of symbolic sign of bringing back together the disciplines of architecture and engineering into one field, and pushing for a synthesis of these fields in the search for ultra-light systems, like you can see in this adaptive shell, where the And I hope you can see the videos running, where by using of high technological devices coming from automotive and aeronautical industry, with the use of sophisticated algorithm, it is possible to reduce the stress utilization of this very slender wood system, and allow for a shell structure, which is already actually a very optimal system, but it's optimum for one configuration, to adapt its shape and become an optimum for several configurations. And another very promising field of work, which is still on our agenda, is the optimization not only of the outside shapes, but also of the inside by using gradation. Also, this is a technology that has been explored in other fields, but it has been investigated for the first time more than 20 years ago in a concrete structure at the ILEC, and it's now, after more than 20 years, leading to very important results, and we hope that it will be transferred into architecture very, very soon. You see here prototypes which have been designed by Daria Kovaleva for the Rosenstein Pavilion as an example how this optimization of shell systems in terms of the optimization of the cavities and where to place the cavities, together with a search for a direct chain from design to production, can lead to very interesting architecture, and I believe that there would be a lot of space to that. Now, coming to the end, let me just quickly show through a couple of my personal work, first starting as a PhD student, done at the ILEC, you see the institute at the background, and my very first prototype of a glass shell, just 1 centimeter thick, 8.5 meter span, showing how glass could be the new concrete in a way, and how it can be possible to reach a new level of transparency by completely avoiding steel. So it's the next generation. The ring is just made by titanium in order to have movement of this system just following temperature excursions. And moving into tension element, then the work that I've been doing on the facade facing the birthhouse of Ferrari, the new Enzo Ferrari Museum in Modena, something I'm particularly proud of since I'm from Italy, and it was one of my first projects. I'm glad that it makes this clear, visible link between sport car and its design and its approach, and it's willing to push the boundaries and optimize amount of material, but also in this willingness to create astonishing shapes out of it. And this has been made possible. The roof has been engineered without any expansion joint, out of aluminum elements fit to place. And it is all based, and now we are getting back to the approach where working together with contractors, in my mind, to achieve these kind of qualities. Here we've been working together with a contractor to make that possible, developing the details and using an extensive making an extensive use of parametric engineering and scripting to design the still system in a very simple way. And the sophistication is behind in the scripting in a way. So when you come at the site, all these laser cut systems with custom placed boards, it can be easily installed together, and at the end of the day, it provides the shapes which is wished and required. And this a similar approach has been used by what I call the next generation of shell structures, concrete shell structures. There's been a long time where shell structures have not been built anymore because their casting has become very expensive. So we cannot use the same technology as it has been done in 20th century. We have to reinvent that. And once again, using scripting, it was possible to be economical in the way that we define the shapes of the different rebars. The colors that you see on the left is not just as a nice diagram, but it's every color is indicating a different shape. And the color grouping that you see is a way of optimizing these shapes within certain parameters and certain boundaries. And I believe parameters are nowadays one of the key tools that will allow for such complex systems to be built within a reasonable economical frame and still leading to resource efficiency in a different way. And the last generation is the Kuwait airport, which I've been working on over the last 5 years before joining the ILEC as the new chair. Also here, we are talking about a much bigger surface, it's 320 square meters. We've been working tight together with the contractor. And now when you see this picture, think in a moment that all these steel truss are not going to be there, and we will have only this beautiful shell system which are tight, connected one to each other. The steel element will be dismantled. They are just temporary structures, and this is just a scaffolding system in a way. So think how this roof will be without the steel elements in the future, because this is just a temporary element supporting as a scaffolding. It is allowing now for the next generation of concrete roof to be erected, since these elements are casted by so-called adaptive molding systems. So the same machine is able to cast different forms. I cannot go that far in detail right away, but this is by using this development, using digital fabrication tools tied to engineering and design, it is nowadays possible to think about the next generation of concrete roofs that makes this very efficient system economical and feasible again. So just to close that, what is the future of lightweight system and what are the challenges? As you can see through all these examples, the basic motivation for lightweight system in the past has been generating iconic elements, making bigger spans possible, make a very reduced use of materials to achieve high elements. But I believe this has been a very reduced field in the past. And now we have the chance, but the necessity as well, to bring these approaches into a wider field. And why that? Because we have the necessity of reducing the emissions. And it is now, I think, agreed about everybody that we have around 20 to 30 years to reduce the emissions. And only the building industry is achieving already more than 40% of the emissions. We have already a problem about use of sand, for instance, and copper and other metals. And if we keep going like that shortly, I mean, just think about copper. It has been doubling its price within this year. And we cannot just keep going producing architecture, building, and then dismantling and wasting that. It's a luxus that we cannot more be responsible for. And now I think we can touch base on the principle that have been and the way that has been showed in the past. And our responsibility is to show a wider field of application of that. It goes beyond just shorter spans, bigger spans or high towers. And this is a bit what we are trying to do at the university also in terms of research fields. On one side, we are sticking with adaptivity, so using, as it has been done in the past, using an actor system, so like muscles, if you want, in a human body, to make structure specifically light. And this is possible for new structural system as this tower, which is 36 meters high. This is the result of the last 4 years of research of an interdisciplinary work at the University of Stuttgart. And you see in black how the system will behave without any adaptation, and in blue how the system behaves if you adapt that. That means if you have the muscles activating it. And but you see also here that we think that adaptivity is not only about adapting structures and allow for, let's say, more than 50% of optimization for the structural components, but it's also about facades. And by working on facade system, as you can see on the right, with a smart facade system, that's a liquid crystal solution. It is about use of energy within the space, so it's about performance, but it goes much beyond that. It's about a new kind of architecture. And if we think how dynamic our life nowadays is, and how static part of the architecture is that we are living in, also in terms of retrofitting existing building, we have the chance of using this kind of solutions and technology to generate a new kind of much more dynamic architecture. And this is what we are currently working on, and what we believe is going to be one of the possible ways in the future. And if you think about concrete and mineral elements, there are a lot of people working with wood, which I believe it's a good thing in terms of ecological footprint, but you cannot just substitute all our structural elements just with wood, because we don't have all these forests, right? And we couldn't have. So we have to use wood where it makes sense. We have to still stick with steel in certain application. We have to use concrete in other application. But the question is how we can make concrete more sustainable. At the moment, we know that concrete is responsible for 6 to 8% of the production of CO2. And this is something that we cannot stick with. So at the moment, we are working with biomaterials and bacteria in order to have the cementification process activated not by a chemical reaction, but which produce CO2, but by bacteria that don't release CO2. And this is a project we started this year, and we believe that this is also one of the future of lightweight in terms of not only of material performance, but also in terms of the light footprint, ecological footprint of our architecture. And this is, in my mind, the future. And looking to the future, we have to make a totally different use of existing resources and materials. And what it may look like a kind of artist's installation, it's nothing else than a waste area for, or a center of collection, better said, for aluminum element. But the nice thing about that is that all these aluminum elements will become facade profiles in a second life. They will become leathers, they will become bicycles, they will become other things. And interesting enough, aluminum is considered to be a material which is expensive in terms of energy production. But in this case, the energy which is needed to provide this material with a second and a third life is coming from the water industry, from waterfalls. And by doing that, it is also the energy, it's coming from the nature. And this approach makes me confident that there is a space for lightweight, a different lightweight approach where we expand the research for resource efficiency into a much wider field, and we just not confine the use of these approaches to some nice, wonderful, iconic elements. But by using the proper processes, we come to a very wide use of these approaches. And this is actually where we see, where I personally see the future of lightweight system, and where we are bringing our energies with a very dynamic and young group of interdisciplinary group of engineers, architects, different scientists together to make this possible in the future. So I'm now at the end of this long excursus, and I'm very open for coming discussion.
Thank you very much, Lucio, for this great talk. I think before we could open the discussion, we have a technical question from Lydia Yuzapolska. She's asking, what is the build-up of the roof of the Ferrari Museum? And if it's possible to make on the roof the greenery, so it could be a green roof.
So it is an additive, the roof build-up, it's an additive system. So we have corrugated steel on top of steel trusses. And then we have foam glass as thermal insulation. Then we have our waterproofing level, and on top of that we come with a second level of waterproofing, which is our aluminum roof, and that kind of special details I've been showing. So in general, by using this additive approach, of course you can have different kind of final roofing devices on top of that. Yes.
Thank you.
Actually, just to address that further, we are currently working a lot in terms of praxis experience, in terms of green facades and green roofs, and there are nice examples coming in Germany on these. One of that is in Düsseldorf. It's called Köbögen with a friend architect, Ingenoven. And the other one is in Stuttgart, where we are bringing green in the city, in the center of the city. So I believe this is one of the future development of this.
Thank you. Litkin Sergey is also asking very technical questions, so let's go through it first. At what time the trusses can be removed at the Kuwait airport under the shell?
We have defined a very careful staging analysis, and it is so once that a shell element is placed in position, it is tied together by the bolts. The main bone system, which is prefabricated, pre-tensioned concrete and steel system, I didn't go that far in detail, and the temporary towers are taken out, then the system is then tied together and it's working. And at that time, then you can take this, you can first take the cable, the tension element of the hatch, release that. Okay. Okay, so first of all, we place the concrete the concrete backbone. So that means we have arches, concrete arches. Let me go back to the slide. Yes. So if you see there is a field and there is an arch covering actually at the two edge of this field. And this arch is the main structure. You can imagine this arch creating the boundaries also of the shell model that is on the left side. So this is what I call the backbone. That means it's a system of arches that it's pre-stressed, and as it is done in bridge systems, and this is the main structural item. This system of arches is stabilized by the shell roof, which is the second element. And this roof is placed on top of these arches, these steel arches, and it is then tied together by means of boards with the technology that you can see on the left bottom. And once you place everything in position, then it is about pre-stressing the arches to the final level, and then the system is tied together. The arches and the shell is tied together. It is connected. You have a connection between the roof and the arches, and then you can release the steel elements, because then it is working as one system, arches plus shell roofs. It is a process that takes around 1 year in a way. So we've been already releasing the first base, the smaller one. So if you look at this picture, you see that the base are changing parametrically, and the smaller base have been released already.
So there was a question about the shell roof, оболочка, оболочечная кровля. Значит, есть основные арки и второстепенные панели покрытия кровли. Арки затягиваются, потому что они собраны отдельно, все панели производятся отдельно, потом ставятся на место, и все это вместе затягивается так, как они держат друг друга. И вот в этом виде уже после этого можно снимать фермы, если я вообще в тот канал говорю. So that was just my small comment on that.
Okay, good.
So when all the panels will be assembled and the whole roof, оболочка, shell roof, оболочка кровли will be post-tensioned, преднапряжена, то есть полностью затянута, and all the panels will be connected to the arches, to the main arches. Okay. Thank you very much. I think that was, yes, all the technical questions. Then we have a little bit more broader question. First, that's from Tanya Gurova. First, thank you very much for the lecture. The question is, how could you shorten or minimize the ecological unfriendly processes when you construct such lightweight structures? I don't know if Tanya was referring to the recent examples or generally to the lightweight structures. I think it's a question of ecology of production, so the footprint of the production processes of such structures.
This is our ambition. And in order to do that, we cannot just look at one aspect of the process. And that's why it is a methodological question. We have to look at the overall chain, from design to production to erection, but also look further in terms of how can we design these elements to be readapted in the future, how can we extend their lifetime, and how can we make sure that at the end of their lifetime, the resources that have been in a way trapped in the system can be reutilized again, as I was showing in my last picture. So this is a huge field of investigation, and we are bringing together all the people that are interested in covering a part of that, because it's a huge research work, and we try to do our part. But we are, of course, have to share energies, and I think this is a process that will take the next 1 to 2 decades to be approached in a scientific, but also in a design-oriented way.
Thank you. Dear guests, please send the questions on whatever language you want. Meanwhile, I have a question a little bit broader also, more related to the context. So this exhibition that is currently ongoing, where we consciously with the students took time to look into the historical buildings. And you showed here really well how evolutionary this process looking like and very consecutively developing. But nowadays, this is normal that you have or historians who are looking into the history or advanced architects and engineers who are trying to solve the problems for the future. Is there any place from your point of view to look in both ways? And as you mentioned, for example, you can find an inspiration in the past, but maybe something more, or still some strategies that you could apply, especially in our non-sustainable time as we could see it?
Yes, I believe that we cannot look at the past like we go to a museum and we see, okay, this is nice, but that belongs to its time. We have very challenging questions that we have to face, and we need a manifold of solutions to address these questions. And I'm looking at it in terms of the ecological future perspective that we have in front of us. And since I don't believe that there is one answer to achieve that, and I believe that would be very sad if we would have only one answer to that, we have to look into in a kind of 360 degrees field and looking how these challenges in different time have been solved by other people, but of course interpret the historical context where this has been happening. I mean, I believe that the work of Shukhov would be done in a totally different way today, as I believe that the ripped shell from Pier Luigi Nervi would be executed in a totally different way. And as you can see, the technological solution that I'm showing for current projects, even if it has a certain link to the past, is totally making use of different tools to achieve or to reinvent solutions. So I believe that for me, the past is a source of inspiration. It's methodologically, it also a source of thinking. And whenever I spend time looking to the past work of people and also learn about their human background, the way that things come together, I see parallels and I see ways how that can be reinterpreted today. What I believe we've been missing over the last decades is too much the willingness of pioneering. And I believe if you look at a lot of our cities all around the world, there's a lot of architecture which has been just following economical, but short-term economical targets. And most of the time, this is not really nice architecture which is coming out of it. It has been following just other targets. And now, and when I look at the way that these talented designers, no matter if engineers, architects, or other fields, when I look at the pioneer spirit, to me, it's not only just looking at it as a source of inspiration, it's kind of giving me personally the energy to push also in my current work, and this is also what I can try to transmit to the people I get in touch with, the same pioneer spirit. And when I started my work as a chair of the Institute around 1 year ago, I started saying that for me, tradition in terms of one eye in the past and innovation, which means in a way one eye or one direction to the future, they are closely linked together. And you can much better create innovation, at least from my perspective and in my mind, if you see how past generations have been doing that. And there are a lot of parallels that we can learn from. And that's why I do agree that it's a good exercise for the students, but believe me, also for the teachers, to look into the past, but not only to fix these into the past, but also to translate or use these and translate in different ways into the future.
Thank you. I also had in mind the work of Frei Otto, who was very revolutionary pioneer at that time, but he published also in his IL publications a lot of historical investigations into traditional society, huts and houses, and as he called the old builders. And I think it's totally doable when you can look backwards and forward, and also, as you said, to take not only the inspiration, but also some part of methodologies. I think we are warming up, and next question is also somehow related to one of mine that I wanted to put at the end, but here it comes. It's about actually the destiny of classical Leichtbau, lightweight structures. The question from Valentin Grudsky. First of all, thank you very much for the lecture, but there is a feeling that the examples of lightweight structures from the beginning of the century or the second half of the century are not frequently or not used anymore. But however, they look lighter and a little bit like a pioneery than the contemporary counterparts. Is it related to that it is very complicated to calculate them, or it is very complicated in building them? Or maybe they are not aligned with the tasks of investors or economical requirements. I think this is just a real provocative question, but I think it should be asked.
That's a very good question. I believe that it is related to the economical shifts of our current time. So in general, it was in the past, it was much easier to be more advanced in the detailing, in the optimizing the use of materials, just because materials were much more expensive themselves, especially technological materials, as it was still in the 19th century, or concrete in the 20th century. Concrete was not expensive, but the point was the man work was very cheap. And at a certain point after the 50s, the 60s, this has been turning around. And the point about that was that we got, we believed that we could, and that we could extract material endless from the earth. And since extracting, sand or extracting other materials, special mineral materials, was very cheap, we thought that it's actually not, I believe it's not just a thinking, I mean, that the economical push, in a way, and the economical interest has been making, let's say, just to make an example, a flat slab much more economical than a ribbed slab. Yeah, and this is even though a flat slab is using double as much material than a ribbed slab. Yeah, so this is the first aspect. The second aspect, which was a bit already inferred in the question, is that calculating these structures is becoming more challenging in the second half of the 19th century. So in a way, then we have to have then this. Sorry, I got just somebody inside. But the use of material is now coming to a turnaround point, because now it's not only about the extraction of this material, it's also about the ecological footprint. And it's about that some materials, as I was saying about in copper, for instance, are no more that much available. And now we are understanding that it's not only about the extraction costs, it's about the overall cycle. And I believe that this is why I see personal a chance for this, for a new type, a new renaissance of resource efficiency, because now we are not looking into resource efficiency and into cost of materials related to a cost of the main works, but it's also the overall balance of these solutions. And the fact that we have not that much surface around the cities where to put all our waste. And we understand that it cannot be just a linear process, but it has to much more to working in a circular approaches. And I think this is the basics where I believe that in the future, a new renaissance of resource efficiency will be allowed, but it is to be reinvented. We cannot think to repropose the patterns and the samples of the past. This is what I was already in a way inferring before. We have to reinvent a new kind of architecture and provide the methodological tools to demonstrate that this is more sustainable.
Thank you. I think this is the answer that a lot of people are usually waiting for, right? Also, because it is not so trivial also in this discussion why the first generation of lightweight structures somehow decreased in the volume and what's going on now. And thank you for addressing that. And
then,
yeah,
let me perhaps add something to that, and that's why I believe it's important that these questions are engaged with a close eye to architecture and to the build industry, because at the end of the day, I mean, look at these examples, yeah, like the Ferrari Museum or the others. At the end of the day, you have a client that has to pay for that. And it will always allow for a certain frame in certain cases, but will not go that much beyond that financial frame. So we all have to face constraints in terms of the financial frame and budgets. It's not only about academic research, but it's also about building architecture. And this is why, to me, research has to be further linked to praxis, and what you learn from the praxis brought to the research and then brought back. And by doing that, then you can follow the right questions in terms of research working.
Okay, we are moving along provocative questions. Now they come to concrete structures. We have two that close to each other. So first is why there is so high percentage of reinforcement in reinforced concrete space shells. I think it's about Stuttgart 21. So maybe if you could come back to this, how you could achieve the economic effect in such projects, or it's not about the economy.
So it's eventually hard to be believed that this system is economical. I can understand that provocation. But at the end of the day, if you think about the size that you have to spans and the amount of columns that you have and the bending that you would have otherwise, this is still in terms of the amount of concrete that you use related to amount of supports that you have an economical solution. And this is due to the fact that the forces are not, it is not just like that, right? Where you have a problem in classical bending, problem in classical punching problems for the engineers among you. But it's more like there is a continuous flow of forces. And yes, I do agree that there's still a lot of space to make this structure more efficient. And I do agree that there is space for making the reinforcement of these elements more elegant. But again, we have to work with constraints. So in other times, I would have been thinking about different ways of reinforcing that, or probably ways of using rib systems just to create a link to past projects and to possible alternatives. But we are not yet so far that the scaffolding of this rib system is more economical than putting more steel inside these shells, right? And actually, the shell edge is just 30 centimeters thick, so they are very slender. But on the other side, if you look into this kind of solution, that goes more into this direction. So you have just 16 centimeters concrete, and the rib is created by steel. And by doing that, you are using both materials in a much more optimum way, and it's not just the full amount of material. But if you would ask me, I could tell you there's still a lot that you could do to reduce the amount of concrete and the amount of steel there. So when I look at these examples, they just show me one step onto a path. But I see still a lot to be done to push this further.
Another question, and I think it's good that you're on this slide. So we are still on the concrete. And I think it's a second question towards the substructure. Sorry, the previous lecture question was from Yelizaveta Agafonova. Thank you very much. Now it's from Daria Manjula. Thank you for the lecture. When constructing such structures, for example, like airport in Kuwait, it is used a lot of additional or scaffolding constructions. Can such structures or substructures be unified or reused? Mm-hmm. If the structure is unique, so from the point of view of ecology, could you account for the construction, recycling, reuse of such additional substructures and their effect on ecological footprint?
Yes, first of all, let me tell you that actually what you see here, it's much better than what it was proposed in the original design from Arup. Because at that time, they were suggesting that you have, at every single node, you have one vertical element supporting that, which is a huge amount of steel. So it's a kind of classical scaffolding system. And we said, this doesn't make sense. And it's also a problem of operativity during construction, because then you will have a lot of vertical elements all around. So I believe that still, I mean, you have to think that what you see is spanning 45 meters. So just bring them in the proper scale. And it is a truss. Said that, yes, it is possible to adapt. It's a truss system, so you can adapt it to different geometry, and you can reuse this. And said that, the steel is a material that you can reuse, recycle in a very easy way. And that's why I believe that the scaffolding, as much as our production system can be reduced, can be reused in a better way. And the scaffolding, the adaptive system I was referring to, the nice thing about that is when you make scaffolding for concrete, then you just have to, you waste most of the material at the end. Here, you have a machine and you just reuse it as much as you want. We have 80 of these machines and we produce 37,000 panels. And the good thing at the end of the process is the machine is still working. They can be used for anything else. So I believe this is also a contribution to a more ecological approach. But this, as again, there's still a lot that has to be done.
Thank you. So now it's a question about the current research in ILEC from Ekaterina Stavskaya. Good evening. Can we know a little bit more on the experiment with the glass shell and the Titanic ring? Which dimensions of the structure are we talking about? Did you continue to develop such research? And the second question is about the functionally graded concrete. How do you think, what are the perspectives of use of such material in the future? And what do you think, when or if or whether will it be used everywhere?
So, okay, on the glass shell, the technical details, I mean, as I was saying, the glass is 1 centimeter thick. It is laminated. It's 8 millimeters plus 2 millimeters laminated. It's the lower level, it's chemically toughened. It's a technology coming from the aeronautical industry. So this way, we have a very thin laminated glass. In a way, it is what you see or the basis for windshield, for instance, in car or in the train industry or in the airplanes. The titanium is shortcutting the forces which are coming from the shell. And if you remember, that was one of the principles I was referring to. And the reason to use titanium is that the expansion coefficient of titanium is the same as the one of the glass. So that means that if you would have used steel here, which would have been more economical, then you would have got thermal constraints, and that would have been translated into more thickness, which is what we try to avoid. And that's why we make use of titanium. And the element, the vertical element, are actually used as a compression element. Usually they are tension elements. But since we are using them as a small, like 40, 50 centimeters high, then it is possible to keep them very thin. So just to recall. Yes. Yes, where should I start again? Okay. Okay. So this is about the shell. I hope it addressed the question. And talking about graded concrete, we see a big field of, wait, it was before. We see a big field of possible usage for the mesogradation on, for instance, as an alternative for slab solution. Just by using big mineral hollow spheres, you can have big cavities. What you see in the image here on the bottom right, it's more microgradation. But we discovered that if we have bigger holes, as you can see in the picture on the diagram on the left below, so I go with the mouse here, then you have a much better relationship between hollow sphere, empty spaces, and full material. And that's why at the end of the day, it's lighter. We're talking about 50% of resources. So this is, slabs is responsible for one of the biggest, in high-rise architecture, one of the biggest use of concrete. So we believe that in a moment where we reduce the amount of concrete for slabs, then we can have smaller columns, we can have smaller foundation, even the foundations can be done out of graded concrete. And we are currently working on a prototype that will be built within the next 5 years, that will showcase how this will be possible on one side. And interesting enough, in the meantime, we work together with investors that are willing to go this way. So there are some investors interested on sustainable architecture, and that will allow to show this technology. So this is talking about classical elements like, slabs or columns or foundations. But of course, on the meantime, we are still thinking about shell systems or shell behaviors to be brought to the next level. And if you now think about using recycled concrete ingredient for these systems, now suddenly you get the second level, because you have a system which is already optimized, and by using materials which are coming from the circular economy, you optimize the ecological footprint twice. And this is also one direction we are currently working on.
Thank you. I think that was all technical questions. So now we come back to the bigger perspective. One question from Mark Umans. I will read the original language because I'm afraid that I could misspell something. Thank you very much for the presentation. You presented a history of lightweight structures, Toroha, Eiffel, Nervi, Frei Otto, some attitudes which were always connected to material and technological principles related to a cultural context, questioning a limit of its time. In the research of lightweight, what would be an ideal technological context to reach it? Should it be related to a question of structural art or elegancy, as it has been by historians as Billington, for example, when analyzing the bridges of Maillart? What is the ideal environment for the future in the construction world and economy?
Oh, wow. So, I believe that the path that is connecting all of these experiences is the search for using less material in general. And it has different historical backgrounds in the different phases. And the connection between these experiences is actually this. So there were a time where it was about scarcity of resources, or it was about the fact that manpower was much more expensive and less expensive than optimizing solutions. Now, the scarcity of resources is a different character. It's more related to the ecological challenges that we are facing. But this is something which is coming back. I don't believe that it's about no more about just structural art. I believe that the field that we are talking about, there's been a time that it was the investigation of talented engineers with a certain degree of, or with a high degree of aesthetical quality, but it was, it has a kind of deterministic aspect to that. And that time, that kind of art of structural engineering, I believe that cannot be repeated in a similar way as it has been in the 20th century. And I think the challenge that we are facing, it goes beyond creating a nice structure with and competing for whom is doing it with less material. We have a totally different target nowadays. And it is more about, and it is what I was trying to explain before, it's targeting not just a couple of iconic systems, and like, you know, a racing car, and making a wonderful prototype, but it still remains one prototype out of hundreds and millions. But we have to work in a wider methodological way, because if I just create one shell, which is very thin, but then around me there are so many classical architecture which is still done in a traditional way, then my target of reducing the ecological footprint is definitely not achieved. So this is, I believe, the new challenge and the future challenge. And that's why when I talk and I give lectures on lightweight system, and I create a kind of historical link, I talk about classical architecture, classical lightweight systems. This is what I show for the past. I say that there is I see that there is a more technological lightweight, which is what Werner Sobek approached in terms of ultra lightweight with adaptivity. But I see the challenge of our generation in facing the next level of lightweight, which is what I call extended lightweight, which means lightweight in terms of ecological footprint. And the three fields are not always bringing you to the same result. If you think about composite materials, for instance, which are a lot used in different fields as lightweight, classical lightweight systems, in terms of ecological footprint, it's a disaster. They are because you cannot bring the fibers and the matrix, the polymer matrix, you cannot delaminate it. And this is all special waste. And that's why if we now set targets in terms of what is our priority, to me, the priority of our generation is to look in lightweight, not in the way that the Meister have been looking in the past, but in the way that they leave a different, completely different ecological trace. And that's opening a lot of new questions to the way we approach architecture, in my mind. I hope that was answering all of the questions, which were a bit articulated.
Thank you. And the last question that is related to your future work from Dmitry Kozlov. Thank you for your talk, Lucio. Do you plan to return to Frei Otto's bionic studies of natural systems and structures in order to solve ecological challenges of the future?
I believe that I'm still convinced that nature is a source of inspiration, and but we have, of course, to rethink that. And actually, if you think about circularity, which is one of the focus for me for the future, I mean, the nature is the best example for circularity. So, of course, it is, and it will remain a source of inspiration. But it has to be reinvented in a new way and with new targets.
That were all questions, but I think we took quite a good time for it. And sometimes students in the course of technology are asking, yes, but lightweight structures, they are not used in everyday life. I think your talk and our discussion afterwards gave us a little bit more thoughts on whether they're really used and if they could be used in the future, and why there is a reason that they should be probably used a bit more.
Yes, and I think that was very precious that that has been a smaller group of people sticking with this, even if they were used in very reduced fields. In certain areas, they make a lot of sense. I mean, I've been explaining about automotive and aeronautical, and then they are very relevant fields. In the architecture, they've been very limited indeed. but the work of few people in these fields can now be translated, and this is our ambition. And this is, of course, a very ambitious target, can be transferred to a totally different field. So the work that has been done, sticking with this, it's very precious now to build on.
And coming back to Fritz Leonard title of 1940, lightweight structures is a requirement of our time. I think it still is. The time has changed, requirement is changed, but the lightweight structures are still the requirement of our time.
I think that's the interesting thing about this is that I was reading the original article a long time ago, then I reread it, and then I read later on comments to this article made from Jörg Schlaich, and I know the comments from Werner Sobek. And it is very interesting to see how different generations coming from a similar school, but different generations have been touching base on this, which is now this work, which is now 80 years old, written by a young engineer, 31 years old, and they still see how contemporary these thoughts are. Of course, the applications are totally different, but the work and the intellectual approach behind it, it is still fully valid. And then we just have to grab it further.
Okay, if there is no further questions or counterpoints, I think on this great point and great thoughts for the future for us to come, we will finish the lecture. Thank you, Lucio, very much again that you agreed to give this talk. I think it's a great, let's say, finishing point of our public program also to our exhibition, Anatomy of Structures. And I hope that we continue such regularly events, also on different topics, and that our collaborations in between Institute for Lightweight Structures and Moscow Architectural School will continue. Thank you, everybody.
I'm very happy to support that further.
Thank you, everybody. Thank you, all the guests who came today on this lecture. This lecture will be available on the YouTube, also with the Russian translation. And on this point, I wish you all a very good evening and see you soon.
Thank you all from my side, and thank you for inviting me.
Thank you. Bye.